Hello everyone. We are continuing with our lessons on process design of producing methanol, biomethanol from biomass. In the first two lessons, we have looked at the process synthesis from the gasifier, where we are gasifying the biomass to produce synthesis gas. And then the second lesson, we looked at how do we further process the synthesis gas to get it to the ratio that we require for methanol synthesis using the water gas shift. Then at this point, we have our synthesis gas ready for methanol synthesis reactor. So we are going to be looking at how do we simulate the methanol synthesis reactor in ChemCAD. As we have indicated, the first lesson we looked at the gasifier, where we produced synthesis gas from biomass. And then further, we continue to look at the second unit in the sequence, where we looked at the water gas shift reactor, where we corrected the synthesis gas to the required ratio of 2, the required H2 to CO ratio of 2 as required by the methanol synthesis reactor. In today's lesson, we are going to look at the reaction kinetics for methanol synthesis. Then we are going to look at implementing the methanol synthesis kinetics onto ChemCAD, and then we will simulate the methanol synthesis reactor, and then we will discuss the simulation results. The methanol synthesis reactor is the third unit in a sequence, the third major unit. I have not in detail looked at the separation of water, which we have said that it will just be cooling and then using a flash unit to separate the water from the gases. And then we did not look at the simulation of the AGR. Remember, the AGR is the acid gas removal, which we looked at the theory and available options for AGR in lesson number 2, but we did not look at the simulation of that. So what we are going to continue doing now is we are going to look at the methanol synthesis reactor. We have removed the water in the water sap, and then we have removed the CO2, the carbon dioxide, in the AGR. Now we are only left with hydrogen and carbon monoxide, which we are going to use to produce methanol in the methanol synthesis reactor. The principal reactions that occur in synthesis of methanol from a mixture of carbon monoxide, carbon dioxide, and hydrogen are usually catalyzed by the copper, zinc oxide, and chromium catalyst. The reactions that occur, you have what originally had been thought to be the principal reaction, where carbon monoxide reacts with hydrogen to produce methanol, and then there's another reaction where carbon dioxide actually does react with hydrogen to produce methanol and water. And then because this catalyst, the copper zinc oxide catalyst, does also promote water gas shift, so the water gas shift reaction does occur. If you look at recent literature, it is believed that the principal reaction for methanol synthesis is actually the second reaction, where most of the reaction actually happens via the CO2 path. For the purpose of this design, we are going to simplify our process to look at only one key reaction, which we will call this our key reaction. Our reaction, we only have one reaction where we are producing methanol from carbon monoxide and hydrogen. This will simplify our design process quite significantly. Higher level of study, it is very important actually to consider all these reactions because they all play a role. And as I have said, the recent literature actually proposes that the principal reaction is in methanol synthesis. The actually principal path is this reaction here. Well, we are not going to look at that, so let's proceed. Our reaction is going to be carbon monoxide plus 2 hydrogens form methanol. This reaction is reversible. That is, the reaction goes in both directions. We have the forward reaction consuming synthesis gas to produce methanol, and then the reverse reaction consuming methanol to produce synthesis gas in this direction that is we have written here. So the forward direction will be producing methanol, and then the reverse direction would be using methanol to produce the synthesis gas. The forward reaction favors higher pressure as the number of moles reduces as the reaction occurs. You have 3 number of moles reducing to form 1 mole. So this reaction does favor higher pressures. So as you have looked, you would have noticed from your given data, we are operating at pressures of about 80 bar. And then also from your literature review, you would find out that this reaction does actually, most of the technology licenses, this occurs at quite elevated pressures. The kinetics that we are going to use would be the ones that were derived by Kozinski in 1986, very old set of kinetics. If you look at the recent literature for methanol synthesis, you would find that they all have these 3 reactions that we have stated in the previous slides. Only older literature would be looking at this reaction as a single reaction of carbon monoxide plus hydrogen reacting to form methanol. So we are going to use very old literature in this, because the recent literature, because of the mechanism that has been studied quite significantly, quite in detail, being understood better. Okay, we have been given all the parameters. We have been given the equilibrium constant, the reaction constant, the kinetic constant, which is a function of temperature, and then all the parameters are given here. Please note that we are not given EK in this. We are actually given EK over R. This will become significant at the later stages, why I'm actually telling you this. And then the reaction kinetics, the way they are, it is the forward reaction and the reverse reaction. If you look at this, and then the denominator is the adsorption term, which is basically a resistance term, where you have the reactants absorbing, or the product absorbing onto the catalyst and not dissolving. So this is usually understood to be a resistance in the kinetics. So as you can see, the denominator, it reduces the rate. Note that the rate expression that is given here is the rate of consumption of carbon monoxide. So we are expressing this in terms of the rate of consumption of carbon monoxide. So if you look at the reverse reaction, it will be the rate of production of carbon monoxide from methanol. So the forward reaction will be the rate of consumption of methanol, of carbon monoxide to produce methanol. Adsorption constants are also given as functions of temperature. Also note that we are given, the constant that are given is the adsorption energy over R instead of the adsorption energy itself, the term adsorption energy itself given. So keep note of that. It will become important once we start working with ChemCat too, because we will need to correct this term. ChemCat expects the term to be EB, not EB over R. So you will need to multiply by R, which is the ideal gas constant or the universal gas constant. The reactor type that we are going to use for this simulation in ChemCat is the kinetic reactor. The reactor editing tab in ChemCat, once you have added the reactor and you click on it, it will look something like this. To learn how to enter the kinetic parameters for a given system, you can click help in ChemCat, and then the help window will pop up giving you a detailed information and step-by-step guide on what is required of you. I think it's about a 4 or 5 page details on the kinetic reactor, giving you the units used. It gives you everything, a step-by-step guide. Here we are going to be giving you a summary. If you are in doubt and you need further information, please refer to this document. ChemCat does not have a direct way of handling reversible reactions. So reversible reactions usually have to be entered as 2 reactions, a forward reaction and a reverse reaction. So as you can see, we have 1 reaction, but when we go to ChemCat, we are going to enter 2 reactions. We're going to enter the methanol synthesis forward reaction and the methanol synthesis reverse reaction. In ChemCat, the standard rate expression that is used to model kinetic reactors is given by this rate expression here. This is the generic one. As you can see, this is the kinetic parameter and then the adsorption resistance parameter. which is the denominator. And as I have indicated, as you can see, there's only one term, which is the forward reaction rate of the forward rate of the reaction. So ChemCat does not have the two terms. As you could see in our methanol synthesis kinetics, we had the forward term and the reverse term. For the for this format of reaction rate expression, ChemCat does expect the K factor to be given in this format, where you have the what is called the frequency factor or the rate constant given as a constant, and then the temperature dependency is handled only in the exponential. And then ChemCat that expect you to supply this term here as the activation energy or the absorption energy, depending on which term we are talking about. So as we have said that we need to take careful attention when we are dealing with this. As we have also the absorption term. Similarly, they are also handled in a very similar way, where you have the constant, and then the temperature dependency is handled in the exponential only. This is a very good news for us, because if you can look, the way our rate constants and our absorption constants are given, they are given in the format that ChemCat expects it. So we do not have to do any modification on these constants. The only modification that we will need to do is ChemCat expects the EK term, the activation energy term, as a standalone term. But what we have given it to you, we had bundled into EK divided by R. So which means that for you to get the EK that you will supply to ChemCat, you will need to multiply the EK over R term that we have given you with R, so that what you have now is just EK. That's the only modification that you will need to do for the rate constant. Okay, same story for the absorption constant. We have ChemCat expects it in the similar format that we have given it to you. So what you will have to do is you will need to modify this term, which is given as a bundle up term. You need to multiply it by the universal gas constant, so that you get the energy term by itself. The tab that pops up in ChemCat when you need to enter the information, you will be required to supply the frequency factor, which we said is normally known as the constant of the rate constant. And then ChemCat also would expect you to enter the activation energy, which we said we have given you EK over R, so you will need to multiply by R. And then there's also a beta factor. If you take a few steps back, beta factor is the exponential of the adsorption term. So if you look at our methanol synthesis kinetics, our beta factor is 3. As you have seen here, I've already given it to you. And our kinetics are given in the fugacity. You will be asked to specify the concentration, the composition, which the kinetic expression is given in. Here we are given our kinetics not in partial pressure, not in molar concentration, not in volume fraction, but in fugacity. And fugacity is the effective partial pressure, is the activity for ideal gases. For gases, fugacity and activity can be used as the same term. Very important that the units of your frequency factor and the units of the energy needs to be checked for consistency, and make sure that they correspond to the units that are specified in ChemCat. Every single time that these constants are given, there's usually units associated with these terms. So just make sure that the units are consistent with what ChemCat expects. Okay, also on the next step, while you are continuing to enter the kinetic data, ChemCat would expect you to enter the stoichiometric coefficient, the exponential factor, and the adsorption factors, as well as the adsorption energy and the exponent of the adsorption term. Let's just quickly go back and look at what these are. These are the W, X, Y, and Z for your reactants and products, and then WA, XA is for your reactants, but now in the adsorption term. If you look at your rate for the forward methanol synthesis, you can see that for the rate expression, your carbon monoxide has an exponent of 1, hydrogen has an exponent of 2, and then the exponent for methanol in this will be 0 because there's no methanol in the expression. And then if you look at the adsorption terms, you have the exponent of 1, and exponent of 1 for all these terms, for all the reactants and products. The stoichiometric coefficients, you would be asked to select the components that are active in the reaction. We have selected carbon monoxide as the first term, hydrogen as the second term, and methanol as the third term. The stoichiometric coefficient for the reactants are given as negative. We have one CO reacting with two H2s. So you have to use the negative coefficients to express the reactants since they get consumed. So for CO we'll have -1, for hydrogen we'll have -2, and then for methanol, which gets produced, then we'll have +1. The exponential factors are the ones that you can get from the rate expression here. As we've said, for CO the exponential is 1, and then for hydrogen the exponential is 2. So then you can enter those as 1 and 2, and then for methanol we have stated that it's 0. The absorption factor terms, you are given those, you just have to enter them as the paying careful attention to the units. Usually these are dimensionless constants. The absorption energy, as we have said, we have given you it bundled by division as a ratio of R, so you need to multiply by R to get the actual absorption energy as required by ChemCAD. The exponent factor in the absorption, we have seen that they are all 1, 1, 1. From what I can see, they are all 1, 1, 1. Yes, actually the expression said 1, 1, 1, 1. Yes, they are all 1, 1, 1. So you leave it as it is. They are all raised to the power of 1. None of them is given in a higher power or a lower power. For the reverse reaction, we look at this term now, which if you remember, it had a negative, and then because of the negative this side, the negatives do cancel, so it all becomes now the rate of production of CO from methanol, because it is now the reverse reaction. If you rearrange this equation, you can find out now the rate constant becomes the initial rate constant of the forward reaction divided by the equilibrium constant. So now we need to pay careful attention onto how do we rearrange this term into the format that it can be keyed into ChemCAD. Note that the exponential for methanol here is 1, the exponential for carbon monoxide is 0, the exponential for hydrogen is 0, and then these ones remain the same. I think there's something not right here. This term needs to remain the same. Please accept my apology here. This term needs to remain the same as it was here. So there's a mistake. I've used somehow the wrong term for this. So it needs to remain the same as we had previously. Okay. So now if you look at the rate constant, we know that it is divided by the equilibrium constant, which we can call it Kp. Sometimes it gets called Kp because it is usually the ratio of the partial pressures. We have looked at this when we were doing the equilibrium of the water gas shift. The equilibrium constant for the isolated methanol synthesis reaction without the interaction of other chemical reactions such as water gas shift and the production of methanol from CO2 is empirically expressed by Reed in the 1977 publication as an exponential of temperature. So what you will need to do, you will need to take this term and bundle it up with this term in such a way that it can be represented into ChemCAD. It's not a difficult thing to do. You can rearrange it because, as you can see, the good thing is this part of the term is a constant and this part of the term is a temperature dependency, which is similar to this temperature dependency. So you will just combine those two. However, for the purposes of this design simulation, the methanol synthesis reactor is assumed to operate isothermally at a given temperature. So I would use a simplification where I say Kp can be calculated for the given isothermal temperature and find it to be Kp constant. So then that Kp, you just take the temperature that is given for a reactor and find this value as a constant, and then that Kp will become a constant, so it can be bundled with the Ko to just form one constant, and then this is now the expression that you end up with which now becomes quite easy to enter into ChemCAD, because now your KO will just become your KO divided by KP, which is a constant. And then what you need to do is just handle the AK over R. As we've said, we're giving you AK, then you just multiply by R to get the actual value of EK. Similarly, same as before, we look at the reaction. We know that now the synthesis gets produced, so their coefficients become positive. Methanol gets used up, its coefficient becomes negative. The exponential factor, as we have discussed, these are 0, 0, 1. The absorption factors remains the same, and then the activation energy can be calculated by multiplying the ratio of absorption energy by R, as we have given it to you as a ratio of activation energy over R. So you multiply by the universal gas constant to get the actual activation energy. Then the absorption exponent remain as 1. Please note that this expression as given here is another rate expression which is given in Kuczynski. I have unfortunately copied it wrongly. In that literature that we are looking at, they had about 3 or 4 different rate expressions. So I've somehow used the wrong one. This just gives you the units that, as I said, you should need to pay careful. You need to pay care on how you enter this. The rate constant will come in mole of CO converted divided by kilogram of catalyst used per second. And then your I over R is in Kelvin. So you need to be sure that the value that you use in ChemCAD is in the right units, but you will see that as you carry on. Okay, for the example that I'm doing, my temperature for the methanol synthesis is 548 Kelvin. And then my universal gas constant in the units of kilojoule per mole is 0.08314. The Kp that I've calculated at this given temperature gives me this value. And then this value was given. So all I need to do is multiply it. I need to multiply. This value was given. I need to enter it as it is in ChemCAD. And then the value that is given is E over R. If I multiply it by this R that I have here, the units that I'll end up with will be this kilojoule per mole, because Kelvin and Kelvin will cancel out. Same for this expression. What I did is we're given KO. All you need to do is now find KO divided by KP, which gives you this value for the reverse reaction. The expression for E over R, the value for E over R is given in the data that was supplied earlier on. You multiply it by R, it gives you this value of the activation energy. It remains the same as that one because the value is the same. And then the absorption constants are given. The absorption energies are given as a ratio of R. So you need just to multiply them by R, and then you will get the values. Please note this, for these two, the absorption energies are 0. Only hydrogen seem to play a role in that. So this now gives you the information that you will need to go and enter into ChemCAD. So at this point, we will switch on to the ChemCAD simulation, where we will start to use the values that we have rearranged and packaged so that we can enter them directly into ChemCAD. Before we proceed with implementation of these kinetics into ChemCAD simulation, let's relook at the parameters that we need to enter into ChemCAD. The reaction we're going to look at is going to be at this temperature, 548 Kelvin, and gas constant, we have put it as 0.008314 in the units kilojoule per mole per Kelvin. The forward reaction of methanol synthesis is 1 mole of carbon monoxide reacting with 2 moles of hydrogen to form 1 mole of methanol. The rate expression is given as the rate of consumption of carbon monoxide. The rate constant as a function of temperature is given as the rate constant multiplied by the exponential function of temperature. And we know that in the information that is given, we are given activation energy divided by R. In order to get activation energy, we need to multiply by R. The rate constant, which is frequency factor is given in the units moles per kilogram catalyst per second. And then what we need to do is we need to multiply the ratio of activation energy with ideal constant with the ideal constant to get the actual value of activation energy in kilojoule per mole. The absorption constants, there's not much we need to do. We have the absorption constants given for carbon monoxide, hydrogen, and methanol. And then we are given the absorption energy as a ratio of absorption energy to ideal gas constant. So we will need to multiply with the ideal gas constant to get the absorption energy in units kilojoule per mole. We're still using the ideal gas constant here, which is 0.008314 kilojoule per mole per Kelvin. For all these absorption parameters, we will need to do that for carbon monoxide, for hydrogen, and for methanol to get the actual absorption energies of those reactants or products. For the reverse reaction, where 1 mole of methanol forms 1 mole of carbon monoxide and 2 moles of hydrogen, we are given the rate as the rate of formation of carbon monoxide. And remember what we have discussed, that we will be using the constant, equilibrium constant that we calculate at the reactor temperature, and we get it as a value here that we have shown in here. So this will be the value of Kp constant that we'll be using. So the frequency factor that we are going to use for the reverse reaction will be the rate constant divided by the equilibrium constant calculated at the given isothermal temperature of 548. So your equilibrium constant will be different from mine because you will be using a different temperature. Then your frequency factor that you're going to enter into a ChemCat will now be the one that is divided by the equilibrium constant. The activation energy remains the same, which we just take the activation energy divided by R and multiply by R to get the actual value of the activation energy. The absorption constant remains the same because the term, the denominator remains the same for both reactions, the forward reaction and backward reaction. Please note that in the earlier slides we had made a mistake. So as you can see, I've corrected this denominator to be the same as that of the forward reaction. Coming now into ChemCat, we need to implement the methanol reactor. We remember the reactor is the kinetic reactor, which is here. If you look into ChemCat, the kinetic reactor, you can bring it over and then connect it to the stream that makes the stream from the AGR, which contains hydrogen and carbon monoxide. If you click onto this reactor, the number of reactions that you need to key in, as we have agreed, is 2 reactions because we have the forward and the backward reaction. The pressure that we will use for my data, it will be 80 bar. The pressure drop, I would leave it blank for now, but remember that there's pressure drop for every reactor. For every unit that you need to do, there needs to be pressure drop. At this point, it's not important for my simulation, so I'm going to leave it out. The kinetic rate expression, if you click this, it tells you that you can do kinetic rate expression, the standard one that is built in, or you can use Excel VB to program your own, or you can define for each reaction. So we said we will be using the standard one that is built in ChemCat. The reactor will be plug flow. We are going to have a vapor only reactor. This reactor occurs in the vapor phase. We are going to be doing the isothermal reactor. We said it will be occurring at, let's just go back and note the temperature again, at 548 Kelvin. At 548 Kelvin. Yeah, our reactor is at 548 Kelvin. So we will put that temperature here. It's isothermally. And then here you are given a number of specifications that you will need to do for ChemCat to be able to calculate either the conversion, you specify the reactor volume, or you specify the reactor volume and then ChemCat will calculate the conversion. So let us just start by saying we'll specify conversion. We will start with a very low conversion. We'll continue. It has to be conversion of carbon monoxide because we are given the kinetics in the carbon monoxide form is the rate of consumption of carbon monoxide or the rate of production of carbon monoxide. So I usually want to start with a very low conversion. So a conversion is given as a fraction. So what I will do is I will start with a 0.05, which is 5% conversion. Methanol synthesis conversion per reactor is usually small. Conversion per pass is usually small because it gets limited by the equilibrium. In most cases from the literature, you will find out that it is usually between 15 and 25% conversion. So it's very small or low conversion. So you end up only converting 25% of the CO to methanol. So I'm starting with just 5% to kickstart the calculations to occur. Very important, click on the more specification tab here. Here you have parameters or input requirements that have to do with the length of tubes, diameter of tubes. Let's not worry about that now. The important part is let us look at this. Concentration will say it is in partial pressure. The partial pressure units will be in atmosphere. This will not really be working for us at this point. But the most important term is the activation energy. Which units are you supplying the activation energy is? This is a very important aspect to look at. Our activation energy is given in kilojoules, if you remember, kilojoules per kilomole, kilojoules per mole. So we need to come and click this. If you read the help, it tells you that the energy, the activation energy and the absorption energy are always given in units of energy per mole. So keep note of that. We have specified ours in kilojoule per mole. So then the unit here for energy is kilojoule. The heat of reaction reference temperature, we will be using 25. This is where the basis, the reference temperature for calculations of enthalpies will be done. So as you know, the standard enthalpies are usually given in 25. It's always advisable to use the reference temperature for heat of enthalpies of formation or the heat of reaction at the reference temperature that is always given. Okay, then once we are done, we can agree with that. What ChemCat will do here now, it takes you to reaction number 1, which you will need to specify the reaction parameters for reaction number 1. What we will need to do is we will need to bring this information tab here. Okay, now that we have the kinetic data input and our kinetic data on the same slide so that we can refer to the data template as we are keying in the values in ChemCat, we are in a good state. The first component, carbon monoxide, second component, hydrogen, and third component, methanol. Okay, we have this is the reverse reaction, so we will need to go back a bit. Previous. Okay, we have carbon monoxide, 1 mole of carbon monoxide reacting with 2 moles of hydrogen to form 1 mole of methanol. Sorry, this. Okay, there we go. So the stoichiometric coefficient for this, let's start at the top. The frequency factor, as we have said, is the reaction rate constant. So it is 2.68 to the exponent 9. So you can enter that 2.68 exponent 9. And then the activation energy is 152.99, which is this value here. And then the beta factor is 3. The composition type is activity. We have discussed that earlier. And then the stoichiometric coefficient for the reactants, remember they are given as negative. For we have 1 mole of CO, -1. We have 2 moles of hydrogen reacting, so that will be -2. And then we are forming 1 mole of methanol, that will be +1, +1. The exponential factor in the reaction kinetic term we have 1 for CO and 2 for hydrogen. So we'll have 1 and 2. For methanol is 0. You can leave it blank. The absorption factor are these terms here. You can enter them all. For carbon monoxide, 6.90 exponent minus 2. For methanol, sorry, for hydrogen is 6.19 exponent minus 8. For CO is given as 0, so we can leave that out. The absorption energy for carbon monoxide is 0. For hydrogen is minus 54.96, which is the value here. And then for methanol it is 0. The absorption exponent, all of them, if you see here, is 1, 1, and 1. They are all raised to the power 1. 1, 1, and 1. If you can relook at this again, everything has been entered. Don't worry about the heat of reaction because it will be calculated from the ideal gas state. The reaction has to be enabled for the reaction to be used by ChemCAD. If you click OK, it gives you the second reaction, which is reaction number 2. Also bring it over here so that we have all the information that we need. The frequency factor, now it is this constant that is divided by the Kp constant, which is 4.46 exponent 12. The activation energy remains the same, 152.99. The beta factor remains the same because the absorption term hasn't changed. We are still using activity. Then same order that we had: carbon monoxide, hydrogen, and methanol. The reaction is now reversed. We have carbon monoxide being formed, which is now positive 1. Hydrogen being formed, but is 2 moles, now is positive 2. Methanol being used up as a reactant, which is minus 1. Then the exponential factors for these, they don't feature. Carbon monoxide and methanol do not feature, so it will just be 0. So it will be 1, so it will be 0 and 0, and then methanol is only to the power 1. The absorption factors, they are as given here. We have to key them like we did before. 6.9 exponent minus 2. 6.19 exponent minus 8, and for methanol it is 0. The absorption energy for CO is 0. For hydrogen is minus 54.96, and then for the last term, which is term C, which is methanol, it is 0. The absorption exponent remains the same, 1, 1, 1. Let's recheck again. Everything seems to be entered. Then you can agree with that and ChemCAD will be happy. Then you can start by simulating from left to right. I always say start with the simulation of this unit. So I usually just, because sometimes once the flow sheet becomes too big, you need to run each unit up at a time. So you start with this, then you move to the second, run this unit up, then you run this unit up, then run all of them until you get to the reactor where you get your information for the reaction. So once you have run the methanol reactor, then you end up with your stream here, which will have methanol, hydrogen, carbon monoxide. You need to separate the methanol and then recycle the hydrogen and the carbon monoxide. This will just involve cooling, flash separator, where you will cool to condense methanol and separate it in a flash separator, and then you will recycle the unreacted hydrogen and carbon monoxide to the reactor here. That's essentially all you need to do for this stage. But remember, your flow sheet would be a little bit more complicated than mine, because it will have heat exchangers, it will have compressors, it will have utility streams. If you are heating or cooling, you need to show that you are heating with steam or you are cooling with water. All those needs to be shown. So I expect to see that in your flow sheet. So this answers how we enter the kinetic parameters in the methanol reactor. Once you have run all your flow sheet and you are sure that you are getting the mass balance calculated, you can look at, if you look at stream 9, we are making very little methanol because of, remember, we had put in only 5% conversion. So we will need to come and increase this conversion. Always when you are doing this, make sure that the volume of the reactor makes sense. As you can see, we have 0.8 cubic meters. It does make sense to me to have a reactor that size. If you end up with 2000 cubic meters, maybe it does not make sense, because 2000 cubic meters is such a huge reactor depending on what volumes you are handling. So always keep note that for the conversion that you are getting, your reactor size does make sense. If it does not make sense, go back and check if your rate constants, all the kinetic parameters are calculated correctly. This is where most of us make mistakes. Even if you look at my calculation, you may find that there is a mistake, slight mistake here. I may have not calculated this properly. I may have not entered the right exponential sign. Always make sure, come back and look at the volume of the reactor that you are getting from the conversion that you are getting. If that makes sense, it makes sense. The size, the scale that you are talking about does make sense. So then you can be happy and say, let me increase this to 25%. With the conversion increased to 25%, you can run the flow sheet again, and then you would see that you get a much more reasonable amount of methanol produced. You can see how far you can push the conversion of methanol while still getting the reactor size that makes sense. We here, our reactor size is 4 cubic meters. I still think it's a reasonable reactor size. Then you can try and push the conversion to 30%, 40%, 50%, and see how big your reactor gets. If the reactor gets unnecessarily big, just look at the dimensions of how the reactor is going to be. If you look at the diameter and the length to make that volume, sometimes you end up with a very large reactor. Students submit a reactor that is does not make sense when you look at it when you look at it physically. It does not make sense. You end up with a reactor, maybe say you have a 5-meter diameter and then a 25-kilometer length. That does not make sense. So you have to make sure that the conversion that you're getting and the size of the reactor do make physical sense. Once that is done, then I think your simulation up to this point is satisfactory. Then what you need to do is separate the methanol and bring back the unreacted gases and then redo the calculation. Once that is done, then you can now scale up your production to the throughput that you are given in your problem statement. That concludes the simulation of methanol synthesis for the in the production of biomethanol through gasification of biomass. We will in the next step look at the overall flow sheet